Good to go? Okay. Waiting.
Yeah, you can go ahead. Thank you very much.
Okay. So welcome again. This week's seminar will be given by Arshad Karimbu Vallappil. He is part of the Advanced Engineering unit here at ICE. He received his PhD in 2021 from the Technological University of Malaysia to then go to work for the Medina University in Saudi Arabia and then joining ICE last year. He's gonna tell us about metamaterials and meta surfaces. So the floor is yours.
Okay, thank you. Okay, guys, good morning. Today I'm going to present about metamaterials and meta surface, its application, and the research opportunity in radio astronomy. So you already explained about me. Well, I have completed my PhD in 2021. My area of research is antenna, metamaterial, microwave, and RF communication. I have nearly 16 papers related to metamaterials and antennas in ISI journal. Most of them are 100% of publication in ISI journal in quartile 1 and quartile 2. Currently, I'm working with Mirror project. It's related to the measuring deep soil moisture from the drones. So what is the purpose of this seminar? The purpose of seminar is I have to give a understanding of what is metamaterials, how the metamaterials can be applied to antenna and beamforming network, and how the metamaterial can be used as absorber and invisibility clocking. So these are the outline of the seminar, a brief introduction about metamaterial, then meta surface, and metamaterial antenna design, and metamaterial in RF engineering, and metamaterial for beam shaping, and metamaterial other applications. So what is metamaterial? Why are they called metamaterial? I have just give a brief introduction about metamaterial. It means it's a material which can alter the properties of electromagnetic wave, which is beyond what you have seen in the nature. It means it's an artificial material with two properties like mu and epsilon is negative. And it can support negative refractive index. So you can see that I have divided mu and epsilon into four quadrants. So I'm working in this area like mu is negative and epsilon is negative. If mu is negative and epsilon is negative, the refractive index will also go for negative because n is the square root of mu multiplied by epsilon. So for example, I'm taking a glass of water, and if you put a straw or a spoon, it will be refracted like this. But if the water is a metamaterial, it will be refracted backward. So this is the difference between the natural material and the artificial material what have been created. So these are three properties. One is refractive index is negative, and epsilon is negative, mu is negative, and it will support backward waves. So I'm going to the next slide. How it started? Who discovered this one? This was discovered by, theoretically, it was proposed by Vallappil in 1967. And in 1997, a scientist Penry in Duke University, he has discovered first mu is negative material and epsilon is negative material. In 2000, the scientist called Smith, he discovered metamaterial. And 2003, the scientist called Kalos, he started to apply in RF and microwave engineering. So before going to metamaterial, I'm just explaining what is epsilon is negative. Epsilon is negative means you have to take an array of thin conducting wire, then you have to arrange in the form of arrays, and it has been separated by a distance of p. You can see the value of p should be less than lambda by 4. This is the main criteria for making mu epsilon is negative. Then it has been observed that at certain frequency, you can see that the value of epsilon is negative. So this is the equivalent circuit of array of thin wires. Next, mu is negative. How you can make mu is negative? The scientist taken two array of split ring resonator. This one is a split ring, two metallic ring kept opposite to each other with a gap, and he observed that at certain frequency the mu is negative. You can see this frequency, the real part is mu is negative, and this is the equivalent circuit of that array of split ring resonator. Now, how we created, how the Smith has created the metamaterial. He combined mu is negative by using mu is negative array of thin wires, and epsilon is negative by splitting resonator. He connected together, and he observed a metamaterial, mu is negative, epsilon is negative at the resonance. He constructed like this. He take a dielectric material. This dielectric material top layer is with splitting resonator, and the back layer is with array of thin wires. You can see here. This started to behave like a metamaterial with epsilon is negative and mu is negative, and it's behaving backward waves. So how we can apply this concept to microwave? So the scientist called Kalos, he said that whenever you can make series capacitance and shunt inductance in a microstrip line, it will support backward waves. We need backward waves. So if you can make something in the microstrip line, it will support backward waves. But in reality, we cannot make like this because always the microstrip line is on the top of some dielectric substrate. So there is a parasitic effect of inductance and capacitance. So the final design of metamaterial microstrip line should be like this. The capacity, series capacitance and shunt inductance due to a metamaterial unit cell, and this is the parasitic capacitance and inductance due to the dielectric material. So what is metasurface? Metasurface means the metamaterial unit cell is arranged in the form of array. You can see that these brown colors are metamaterial unit cell. Then if you arrange like this, and it has been separated by a distance of lambda g by 4. So it should be less than lambda g by 4. Then only it will behave as a metamaterial. The primary condition is that one. The size of the unit cell should be less than lambda g by 4. The spacing between the unit cell should be less than lambda g by 4. So this is a primary condition. Then we can make arrange in the form of array. This we are calling metasurface. So two types of metasurface are there. One is reconfigurable, other one is non-reconfigurable. In non-reconfigurable, once you fix the unit cell, you cannot modify that one. But in reconfigurable, you can see the yellow color. This is switches. You can control the metamaterial unit cell. You can turn off some metamaterial unit cell. You can turn on some. So you can control the electromagnetic waves much better than non-reconfigurable wave. So how this is working, I'm just explaining. When there is an incident wave here, it will be refracted backward waves. Can you see? This is the metamaterial. But in normal, it will be go like this. But in the reflection, in normal, is the incidence angle equal reflected angle. But in metamaterial, we cannot predict what is the reflection angle. So I'm mentioning as θ3. So how we can apply this one in the RFI microwave? So I'm just finished the introduction. I'm just going to my work, what I have done. So we have more challenges like electrical, mechanical, cost, commercialization. In electrical, whenever we are going to the antenna, always we will feel a challenge of bandwidth, gain, polarization, isolation, and beam width. In mechanical constraint, how to connect this antenna or this RF components with other circuits, and the size and the volume. And the third one is the cost. How much it will be the cost of fabrication and installation process, then how to commercialize it. These are the challenges we usually face. So what have been done in metamaterial by using metamaterial antenna design? So the metamaterial you can use to improve the gain, bandwidth, reduce the mutual coupling, and reduce the size. So these are the properties we can achieve by using metamaterial unit cell. These are the different type of metamaterial unit cell you can see. And this is one of the metamaterial unit cell used by Kalos for his design of antenna. It will support backward waves. So before going to my design, just explaining what is microstrip patch antenna. This is a microstrip patch antenna. You can see there is a direct. This is a dielectric material, and the radiating patch is on the top, and the ground plane is in the bottom. So what is my constraint is I have to improve the bandwidth, and also I have to reduce the size. The challenges of this microstrip patch antenna is the bandwidth is very low, like 50 megahertz. Gain is less, and also you can reduce the size is okay. The advantage of the microstrip patch antenna is you can connect with any RF circuit, or it is lightweight, it's conformal. So the disadvantage is in terms of bandwidth and gain. So in order to improve the bandwidth, what I have done means I designed a triangular patch antenna, and I applied, this is a metamaterial unit cell. I applied on the bottom of the substrate. It started to increase the frequency bandwidth from 3 to 4 gigahertz. This is the return loss graph of the antenna. What is meant by return loss graph means whenever you are giving the feed to the antenna, how much power is reflected back. So if the value is less than -10, it means most of the power is accepted and start to radiate. So from this graph, you can see that from -10, 3.2 to 4 gigahertz, the value is below -10 dB. It means the operating frequency is from 3.2 to 4 gigahertz with a bandwidth of 800 megahertz. Normally, the patch antenna bandwidth is 50 megahertz. I improved 18 times as compared to the normal patch antenna. So this gives you the size of 1.8 centimeter. Normally the conventional patch antenna, the size is at 3.5 gigahertz. The size is 4.5 centimeter. I have been reduced by 8.8 to 1.8 centimeter. Now the unit cell have been used is a metamaterial. How I can prove that one? So I have been using software Microwave Studio. This is CST Microwave Studio. It's a software to check the S parameters. So many applications it has. So what I have done means I took one unit cell and incorporated the top of the dielectric material, and I defined the each axis. I defined x-axis as waveguide port, and the y-axis as perfect magnetic conductor, and z-axis as PEC. Then after that, I observe my S11. S11 means return loss, how much power is reflected back, how much power is accepted. Then S12 is the power going from port 1 to port 2. By getting this value, by using a method called Nicholson NRW, Nicholson-Ross-Beam approach, we can find epsilon and mu. From the graph of epsilon and mu, at 3.5 to 4, the value shows below minus 0. So you can see it. So I can prove that what has been used a metamaterial structure by using the value of mu and epsilon. Now next one is how you can apply metamaterial in RF engineering. So for that one, I have taken a coupler. This is a coupler. So I have given the coupler to him, so you can see that one. So the coupler means it's a power dividing circuit. It's a power dividing circuit with a phase difference of 90 degrees. So it has 4 ports: port 1, port 2, port 3, port 4. These are the input port and these are the output port. When you give the power to this port, this will be equally divided, 50%, 50%, and the phase is 90 degrees. So what is the problem of this? Is the conventional structure. What is the problem of the conventional? Is the size is big. You can see 4.2. I want to reduce the size and I have to improve the bandwidth. So in order to check the parameters of the coupler, we have 4 parameters. One is return loss, coupling factor, or you can say that transmission loss or insertion loss, then isolation loss and phase difference. Return loss, I already explained what is that, how much power is reflecting back. Coupling factor means how much power is going from this one to this one and how much power you are losing. For example, if you are giving 0 dB, if you are getting minus 3 dB here, it means half of the power is reached here. So if you are giving 0 dB, if you are getting port 2 and port 3 is minus 3 dB, the power is equally divided, and the phase difference should be minus 90 degrees. What I have done means, in order to improve the bandwidth, I applied interdigital capacitor. This is the unit cell I have been used. I applied to the horizontal arm and vertical arm of the branch line coupler in order to reduce the size and improve the bandwidth. And the design of this IDC I have been given here. So the size of the branch line coupler, you can see, is reduced to 2.1 centimeter from 4.2 centimeter. So there is a reduction of 54% as compared to the conventional design. So this is a fabricated prototype. You can see I given to one of the guy. So you can see that this is an interdigital capacitor. This is the size of a coin. It's very small, and you can see that it's operating from 2.6 to 4 gigahertz. But this is a return loss. But we have to consider what is the insertion loss. How much power is divided? This is operating from 2.87 to 4.1 gigahertz. In conventional, it is working from 3 to 4. So the bandwidth is improved by 1.5 gigahertz for the metamaterial based branch line coupler. Here you have only getting 900 megahertz. So 600 megahertz improvement in the bandwidth, and size is reduced by 54%. And the insertion loss, you can see, I said already, it should be minus 3 dB. It's very close to that value as compared to the conventional side. And the phase difference is 90.9 degrees. Now I have been compared with existing design available in the market. From this one, you can see that all other design, they try to reduce the size, but it's affected the bandwidth. I reduce the size, and also I improve the bandwidth by 40.2%. Next one is another component. This one we have to say that switched beam antenna array. What is this switched beam antenna array means? There is a beamforming network. We will connect with antenna array. This will start to radiate 4 beams in 4 different directions with high gain. Normally, if you are taking a single antenna, the gain is less. So in order to improve the gain, have been used array of antenna and connected with the branch line couplers. This started to radiate the antenna in different directions. So once you are making conventional butterfly matrix, you can see the size is 15 centimeter, and the bandwidth also less for the conventional. So I have started to design a butterfly matrix by using a metamaterial branch line coupler. These are the branch line coupler, 4 branch line coupler, one crossover, and two phase shifter will give you a beamforming networks. I'll show the next diagram. You can see this is a metamaterial based beamforming networks. When you are giving the power to this port, there will be a phase difference of minus 45 degree at the output port. When you are giving the power to port 2, there is a phase difference of plus 135 degree. When you are giving to port 3, there will be a phase difference of minus 135. And when you are giving to port 4, there will be a phase difference of plus 45 degree. And the transmission loss should be minus 6 dB at the output port. So these are the criteria for this one. So you can see the result. This is a fabricated prototype of the thing. You can see these are the branch line coupler. This is the crossover, and this is the phase shifter. You can see it start to operate from 3.1 to 4 gigahertz, but the insertion loss is working in the range of minus 7 dB from 3.2 to 3.7 gigahertz. You can see in this range, the value of insertion loss is minus 7 dB. It means all the purposes are equally divided. So you can see the phase difference. When I applied to a port 1, you can see the phase difference, this black one, is minus 45 degrees from 3.2 to 3.7 gigahertz. And when you got given the power to port 2, you can see plus 135. When we give the power to port 3, this is minus 135. And when power is fed to port 4, this will be plus 45 degrees. So what is the advantage of this one with respect to the conventional? The size is reduced by 75%. This metamaterial size is 7 centimeter. The conventional, this is 15 centimeter. So I have been reduced by 75%, and the bandwidth is improved by 8.2 times. And the phase error was only 5 degrees as compared to the conventional. Now what I have done means I connected the antenna with this beamforming network. It started to give 4 beams in 4 different directions with high gain. So you can see that when I given to port 1, the radiating in this region. When to port 2, this is radiating in this region. When I given to port 3, this is radiating in this region. When I give into port 4, this will be radiating in this one. So where I can apply this one? My plan was to apply in the drone because of my first constraint is I have to reduce the size to keep this one on the drone. So once I kept on the drone, this start to radiate in 4 different directions. So the drone can communicate with 4 different devices in the ground communication. Same concept you can apply to radio astronomy, the radio telescope, to scan large area to get more information, and the detection will be much better. Now next one is I've been used split ring resonator for the band pass filter. You can see that I have been used a split ring resonator in the conventional antenna. This is the split ring resonator, and you can observe that when you take in the first step as a triangular antenna, this is start to work from 3 to 12 gigahertz by making partial ground plane. This means ultra wideband. Processing of the signal is much difficult. So what I have done means I have been just made a slot. So it made a notch band. You can see this is only one notch band. I'm getting at this frequency range. I'm getting this frequency. My intention was my antenna has to work in 3 bands like C band, X band, and 5G. The 5G is 3.5. So when I inserted in the step 3 like split ring resonator, it start to work in the 5G frequency. You can see here. Then it's made a notch. Then it start to work in the C band. Then again there is a notch. Then it start to work in the X band. So the advantage of this one is work as a filter with respect to the antenna, and also is given 3 triple band. So how I have to prove that the metamaterial cell, what I have been used is a unit cell is a metamaterial. Have been just designed by using CST Microwave Studio. I defined the port, and I defined which is the magnetic conductor and where is the perfect electric conductor. Then you can see that from 2 to 5.5 gigahertz, the value of n is less than 0. So this is the fabricated prototype. This one is I'm using metamaterial super straight. These are the super straight. You can see here so many metamaterial units I kept on the top of the dielectric. I have already passed the component in that one. So I kept above the antenna. This is the antenna. The antenna is working at 2 frequencies, 3.5 and 5.6. This 3.5 is the 5G frequency. In Spain, it was 3.6. It's working at 3.5, and there is a 5.6 gigahertz. It will be in Wi-Fi 6E. So I designed an antenna is working 2 band, but the gain is very less. So in order to improve the gain, I have been designing a metamaterial unit cell and 5x4 cross-slot metamaterial unit cell. It has been, you can see here, is a super straight. While keeping like this, the gain is improved from 3 to 6. You can see when initially without super straight, the gain was nearly 2.2 dB. When I kept the super straight, this one, the gain is increased from 6 to 7 dB in the range from 3.4 to 5.6 gigahertz. So you can use metamaterial for improving the beam. Next one is a beam metasurface I'm using for beam shaping. First, I have designed a P-band antenna. This one is working at 360 to 380 megahertz. And you can see that this is a return loss. You can see where it is working. The beam is radiating only one direction, but my intention was I have to split the beam into two. So normally your antenna gives you only one radiation. My intention was to split the beam into two. One is to receive the direct signal from satellite. One is to receive the reflected signal from the ground. So you can see that when I kept the super straight, you can see one is here, another one is here. Initially with one antenna, there was only one beam. By using super straight, you can divide the beam into two. Now next one is I'm explaining about absorber. This is not till here, this was my work. And now I'm explaining its others' work. This will be useful for you, how you can use metasurface as an absorber. What is an absorber? Absorber means whenever there is an incident wave on the absorber, it will absorb all the electromagnetic wave at the certain resonance frequency. So it means there is no reflection, there is no transmission. So you can see that one of the scientists, he designed a metamaterial unit cell and kept on the top of the dielectric. This is a dielectric material and this is a metamaterial unit cell, it's a ground plane. And the absorption is very close to 1. It means most of the magnetic field and electric field has been absorbed. How it has been done means the surface impedance of the metasurface matched with the free space impedance. So because of that, there is no reflection and there is no transmission. And this is another one, he worked in optical absorber. You can see the optical absorber working at 126.7 terahertz. He designed a leaf-shaped unit cell and kept on the top of the dielectric. Dielectric substrate here is SiO2, and the metal, still microwave frequency, the metal we have been used is copper. But here, because of the optical, they have been used silver. It can be seen that the absorptivity is increased to 1%. This can be used as in IR imaging system, thermal bolometers and all. What is the advantage of metasurface? Can be used as absorber also. Next one is I'm explaining about invisibility cloaking. So metamaterial can be used for invisibility cloaking. So I was just showing a video of Harry Potter. You can see that when he weared that dress, he is no more visible. His body is invisible. So this is invisibility cloaking. So you can see only the head. So same thing you can do. This is object, and if it is covered by a metamaterial unit cell, you can hide this object. For example, I'm taking just analogy. Whenever this one, the light here, when there is no object, the intensity is very high. When there is object in between this dot, the intensity of the light will be less. But when you keep an object and surrounded by the metamaterial unit cell, the intensity is the same. So you can hide the object. So how you can do the measurement that way? Keep the object and make the metamaterial unit cell and take two horn antenna. One is transmitting and one is receiving. So in the first, there is no object. There is no object is that the transmission is complete. There is no loss. Now we kept the object. You can see there is a transmission loss is there. Next, he kept all the metamaterial unit cell. This can again go back to the zero close to. There is only few changes there, but it's very close to zero. It means there is no loss. Now what they have done means they kept all the mobile phone and everything inside. Still, there is no transmission loss. You can have some PISA seminar inside that also. No one will see that one. So the metamaterial can be used for wireless transfer also. How it can be means that's a transmission coil and the receiver coil. This is a magnetic coupling. So you can see some of the wave is going away from the receiver. If you keep the metamaterial unit cell, it can be redirect the signal to the receiver. So this way we can improve the efficiency of the receiver coil. Finally, some of them are using this metasurface for communication. You can see there is an obstacle in between the base station and user. So it's very difficult to communicate with each other. If you give the metasurface, the signal will be reflected and it will be received by user. Normally, almost everyone using relay. The relay will take the signal again and it will process again. It will increase the cost. And there is an active signal also, active element also required. But here, there's no active element, just passive, and you can reflect it back. Now I'm going to give some some call from NASA. So this is call in NASA in 2020 related to metamaterial and metasurface technology for remote sensing applications. So they call in 2020 related to how the metamaterial can be applied to remote sensing. The topic of interest was beam shaping with metamaterial. I already shown how I did the beam shaping and how we can apply metamaterial antennas, how it can be applied in RF components. Still, they are interested in absorptions, how it can be applied for liquid crystal medium, and so many applications are there. So I covered 3 things in that. Now, how this metamaterial concept can be applied to radio astronomy. I'm showing here a square kilometer array. So you can see that the antenna are densely packed. You can see so many. So there is a chance of interference from this antenna to this antenna. The characteristic impedance of the antenna will be changed. Once the characteristic impedance is changed, it will affect the receiver. The spectral purity will be affected. So in order to avoid that one, you can use a metasurface in between the antenna. It will take all the side lobes. So there is no interference to the other antenna. This way you can improve the spectral efficiency. Next one is the challenges in radio astronomy is the lens, bulky lens. One is mechanical problem is that to take that one. Other one is that traveling, if the signal is traveling to a lens, there is so many lens. So signal is traveling to a lens, there is a chance of degrading the strength of the signal. So you can use meta lens is a size is less than compared to the optical lens. So it will improve the better result. The final one is the wideband high directive sub-terahertz antenna. After, I think I'm not very good in that one, astronomy. After Big Bang theory, I heard that 90% of the signals, photons are in the terahertz frequency range. So we need a high directive antenna. Horn antenna, with single horn antenna, you will not get high directive antenna. So you can use a metamaterial in this one in order to receive terahertz signal. So these are the conclusion about how we can apply this one. So I have been used metamaterial for several applications. One is, I'm going to conclude that one, have been used to improve the bandwidth, reduce the size, improve the gain, and you can use metamaterial for beam shaping, and you can use metamaterial surface as an absorber, and also it can be used as an invisibility problem. So these are the reference I have been used. Thank you.
Thank you. We have plenty of time for questions. So please.
Yeah.
It's the beginning of the talk.
Okay.
Maybe my question was already answered at the beginning. Has this technology been in orbit in satellites? Not yet.
Still under research because it's a very new topic. So no one was not ready to take any risk. So it's still under the process. As far as I know, it's not in the satellite. But NASA is working on that one, how we can apply this metamaterial concept into this one. And almost everything, because it's a very new area. In 2003 only it started at the beginning, and people are working there is a meta lens already is available. So many are using an optical in RF. Still in remote sensing, yes, but in the ground station. But
yes, thank you for the talk.
Yeah.
The prototype that you have shown us, you are using this FR4 dielectric.
Yes. Normally, you can use any type of substrate. So the width and length will be changed according to substrate. I have used low-cost material, FR4. From that FR4, I change the properties of the material to mu and epsilon is negative. Then I extracted these properties.
Yes, what I wanted to say is that if you use another type of dielectrics that are more, let's say, more
expensive dielectric material. Yeah,
you can for RF. Do you expect to obtain a better?
Yes, the design will be changed accordingly based on the dielectric property of the substrate. The FR4, the dielectric property epsilon is 4.3. If you take some other substrate, it can be 2.2, 2.8, all these things. So you have to change the design accordingly. You have to start from the beginning again.
But the result would be better than with
FR4 is the cheapest thing. You will get much more better result if you are using a high-end product like Rogers.
Yep. I have a question. So you build these periodic structures,
yes,
like sticks or whatever. They must be at a distance shorter than lambda 4.
Lambda g by 4.
Divided by 4. What happens if these structures are not perfect conductors? So if
there are structures made of some material that is not as good as copper, for instance.
You can, most of them will work only the electron flow only in the conductive material. If you take an insulator, there is no flow of electrons, so you cannot regenerate that one. Instead of copper, you can take aluminum, you can take silver, you can take gold, all those things. But non-conductive material, so how the flow, will be no flow of electrons.
Now I'm thinking in nature, imagine you have a field and you have your, I don't know, corn crop.
Okay.
They are long structures.
Okay.
They are separate, they are very close to each other.
Okay.
They are full of water and they are somehow a little bit conductive. Can this cornfield behave in some way like a metamaterial?
I cannot say that one. So it's more technical because I didn't check with non-conductive material and also very less conductive material. So I have to work on that one. Then only I can say the correct exact answer. If I'm saying something, it can be good. So in the future, I'll think about this one, how we can apply this type of things. So
big crop circles.
Once the variations, the pattern that was repeated was in the shape of leaves.
yes. It's not my work. I just explained that one. Those who my work. I said where this one I explained to the audience that the meta surface can be used as an absorber. So the scientist, the researcher, he took the leaves of that one, and it has been by using the metal part is silver because the range of frequencies work in the terahertz. Because of that, they use the silver.
But do you know why this shape?
You can take any shape in the universe is available. Then you have to change the properties accordingly.
Last one then. I was a bit confused when you spoke about your work because in the first part you were saying that you wanted to increase your bandwidth.
Yes.
If I understood correctly, but then you showed us a three-step process in which you made it smaller.
Yeah.
So the point is to have a small bandwidth, or just to have control on the band you want.
Normally, for all the things, microchip pattern, the bandwidth is always less in pattern. So I have to improve the bandwidth. So I applied the metamaterial structure. In the same time, I have to reduce the size. So when I'm reducing size, all other researchers, when they reduce the size, the bandwidth is reduced. So without affecting the bandwidth, have been applied the metamaterials.
So you have to draw a compromise somehow.
Yes.
Okay.
So it's a compromise between the bandwidth and the physical size of the circuit.
Any questions online?
Hi.
Chat. I don't see anyone. Well, in that case, let's thank Arshad again.
Thanks all for